As we have said before, the Black-Scholes equation is the same for different options, and what specifies the kind of option we're evaluating are the boundary conditions. So the boundary conditions are determining what's the option that we are evaluating. So that's very important in the partial differential equation that we want to evaluate. So here we're going to present different examples for different kind of options. So first, we're going to start with the call option. That's going to be the first one. So suppose we want to price a call option, then at s equals 0, that's one side, we know that the value of the option is going to be 0. So therefore, we have that b evaluated at 0, j, and any j is going to be 0. This is one boundary condition. Then going to the other side for large S, it means that we are going to exercise the option for very large S, for which the maximum one is going to be S max. So the value of the option at any time will be given by this one. Basically, is S max minus the discounted price of the exercise price. E is going to be the exercise price. Remember, the R is going to be the interest rate. T, capital T, is going to be the maturity time. And the small t is going to be the time that we are evaluating that. So that, remember that this t minus t here, this is what we have called tau. So writing in our index notation, so the boundary conditions corresponding to this one will be the option evaluated at the maximum and value corresponding to the s-axis at any time. J will be given by this one. This is the s maximum minus the discounted e, which is e times e to minus r, and this is the tj. This is the t evaluated at time j, which is j times delta t. So this is the other boundary conditions that we can include in order to evaluate the call option. Similarly, we can have the boundary conditions for the put option. So in this case, for example, we're also going to do the same, analyzing the boundary conditions both for s equals 0 and large value of s. Now, so first, the put option for s equals 0, it means that in this case, we are going to exercise the option. So for any t, any time, the value of the option evaluated at s equals 0 at any time will be given by this one, which is the discounted exercise price. So again, we have that this is the tau time, and that implies that these boundary conditions can be written this way. This is the value of the option evaluated at the index corresponding to the s-axis 0, and the time j will be given by e times e to minus r, and the tau evaluated at time j will be j times delta t. And on the other hand, the put option that becomes worthless for very large s, then it means that for very large s, it means that the value of the option corresponding to the index ns and time j will be given by 0. So these are the other two boundary conditions we do have for the put option. There are specific boundary conditions which specifies for this kind of option that we do have. However, it's also true that we can also have other kind of boundary conditions that will more generally apply for different type of options. For example, here we have a boundary condition that as s equals 0 is satisfied for most of the contracts. So in this case, what do we have? That's a useful boundary condition to apply at s equals 0 for most contracts, including these calls and puts, is that the diffusion and drift terms, they switch off. So at s equals 0, then you have that this is 0, this is also 0. Then what we have is that this is equal to this one. So this means that at s equals 0, the payoff is guaranteed. Then we have that resulting equation is basically this one, as we have said here. And what we can do is we can find the final different representation for this equation here. So that will be the final different representation, as we know, corresponding to the time of partial derivative. This is the one corresponding to the time derivative we do have here on the left. And then on the right, we have minus r times this v evaluated at index 0 at any time j. So from here, we can clear the value of the option evaluated at 0j plus 1 as a function of the value of the option evaluated at 0 at time j. So we have another relation between these times. And this is another kind of boundary condition we can consider that's applied at s equals 0. And actually, this one can be applied to any kind of option. So actually, as you can see here, we might have actually different kind of boundary conditions depending on the and that we can choose which boundary condition we can apply. This one, for example, can be applied to any kind of option we have, and this is the specific one to be applied at s equal to 0. On the other hand, another kind of more general boundary condition that in this case we can apply that at s at the maximum value of s, also for most contracts, is that when the option has a payout that's almost linear in the underlying for very large values of s, then we can use the following boundary conditions. Actually, this is what happens, for example, whenever you have, for example, an European call option, remember, this is something like that, that's 0 up to the strike price, and then it goes linear. So as you can see, it goes linear here, so basically means that here for very large s values, then we do have that the partial derivative of the partial derivative, second order derivative of the value of the option with respect to the asset here, evaluated at very large values of s at any time, it's 0. This is the kind of boundary condition that we can consider, because even though that this is the payoff, we know that if it's evaluated another time, then we have something that goes something like that. So here at very large s, it's linear. So here it's linear. And if it's linear, it means that the second derivative, it will be 0. So that's the condition that we can apply. So again, in order to apply and to find what the relation that in this case, this one it's verifying. So because here we are centered in order to find the boundary condition of maximum s. So we want to find what kind of relation we do have for this value of the option with these two indexes here at any time, at any j value. Then we have to find the finite difference representation for the second order derivative of the value of the option with respect to s. And this is what we have here. This is the finite difference representation for the second order derivative of the value of the option with respect to the asset. This is one, and this has to be 0. This is the boundary condition, considering the boundary condition we have just mentioned. So from here, as this is 0, this basically means that this here in the numerator has to be 0. So if we clear from here this one, because this is actually what we want to find, that's the relation that we do have. That's the relation that the value of the option evaluated at index and s at any time is satisfying. Actually, you can see the relation of this one with the previous ones. So this is the kind of another kind of general boundary condition that we can apply for most of the options that have this linear behavior, very large s, that we can apply actually for large s values. So in this case, the boundary conditions for the maximum s. In this case, that's a relation that we have to plug in our finite difference representation in order to evaluate numerically the options. So here I've just commented on different kind of boundary conditions we can have in order to evaluate the Black-Scholes equations. So that again, the kind of option you do have, it's here, it's included in the boundary conditions that we are imposing to the Black-Scholes equation.